We know from the law of large numbers that our sample statistic is going to be somewhat close to the population parameter, and it gets closer as the sample size increases. But how close is the sample statistic to the parameter? Since we generally don't know the population parameter, we can't say for sure, but we can speak generally about how close the statistic is likely to be using sampling distributions. Recall that the sampling distribution describes how likely is each of the possible values of the sample statistic. In other words, the sampling distribution describes the distribution of results you would get if you asked a bunch of researchers all to conduct the same study with different samples. So if we look at the variability in the sampling distribution, we'll have a sense of how close or far from the population parameter our statistic may be. In this session, we're going to quantify this with something called confidence intervals. But first, let's start with an analogy. Suppose you're at an archery range and a target is tacked up on a board, but the person who tacked it up on the board wasn't very careful and it isn't exactly in the center. Someone shoots a few arrows at the target, and you can see from the back where the arrows went in. Just looking at the back, can you figure out where the center of the target is based on the location of the arrows? What would be the best guess for the location of the target? Well, it would be the center of where you see the arrow shots. Now, the target isn't going to be exactly at the center of a few arrows, but it will probably be close. We can draw a circle around the arrows to show a region where the target is very likely to be. If we clear away the arrows and the person shoots again, we'll get a new set of arrows, but these arrows will be in slightly different locations. Do you think the center of the arrows, our best guess for the location of the target, will be exactly the same? Probably not. Each time the person shoots a set of arrows, we'll get a slightly different guess for where the target is, and a slightly different region in which the target is likely to be. But they'll all be pretty close to where the target actually is. Now, what happens if a more or less skilled person steps up to the target? If a less skilled person shoots a set of arrows, the arrows will likely spread out, since the less skilled archer probably isn't as consistent in their aim. As the spread of the arrows increases, the circle we draw around the region where the target is likely to be will get bigger. On the other hand, if a more skilled person starts shooting, the arrows will likely get closer together, since the more skilled archer is probably much more consistent in their aim. The arrows will be closer to the center of the target, and we can draw a smaller region in which the target is likely to be. It might seem kind of silly to try and figure out where the target is from the back of the board. Why not just go around to the front? Well, in statistics, the target is like the population parameter. We can usually never know it directly, so we have to figure it out based on our sample. Those are like the arrows poking through the back of the board. When we use a single sample statistic to estimate a population parameter, we call it a point estimate. This is a single number that's our best guess for the parameter, and it's usually based on a sample statistic. In statistics, we often write a point estimate as the same letter that we use for the population parameter with a hat on top. So if we're estimating the population mean, we would take mu, the letter we use for the population mean, and we put a hat on top to show that it's not the actual population parameter, it's the point estimate for that population parameter. Similarly, if we're estimating the population proportion, we would take the letter P and put a hat on top to show that we aren't talking about the actual population proportion, we're talking about a point estimate for the population proportion. Typically, we use a sample statistic as the point estimate for a population parameter. For example, we might use the sample mean to estimate the population mean, or the sample proportion to estimate a population proportion, or a sample correlation to estimate a population correlation. Now, since it's a single number, a point estimate doesn't give any indication of how close it's likely to be to the parameter. It doesn't contain any information about how much error there might be in the study. Instead, we can provide a confidence interval. This is a range of values that would be most believable for a parameter for a given level of confidence. The confidence level indicates the proportion of such confidence intervals that actually include the population parameter. Think of tossing a ring around a post. If I give you a ring of a certain size, you could toss the ring toward the post a bunch of times to try and figure out how often you can get the ring around the post. If I give you a larger ring, it would be easier to ring the post, and your proportion of successes would go up. On the other hand, if I gave you a smaller ring, it would be harder to ring the post, and your proportion of successes would go down. If we had a lot of time and patience, We could keep trying different ring sizes until we found the size of the ring that you would need to ring the post 95% of the time. In this analogy, the post is like the population parameter, and where your ring lands is like the sample statistic from one study. The ring is like the confidence interval. Each time you conduct a study, that is, you toss the ring, you can calculate a confidence interval. Sometimes the interval will include the population parameter, that's when you ring the post, and sometimes it won't. The size of the confidence interval, that is the size of the ring in our analogy, determines how often that type of confidence interval will include the parameter. The size of the confidence interval is called the margin of error. This is half of the width of the confidence interval. That is to say, it's the distance from the point estimate to either end of the confidence interval. The margin of error gives a general indication of how close an estimate could be to the parameter. If the margin of error, the width of the confidence interval, is small, then the point estimate at the center of the confidence interval is most likely to be close to the parameter. If the range is large, on the other hand, there's considerably more uncertainty in the study. That is, if you repeated the study many times, there would be much more variability in the results you obtained from study to study. Note, the margin of error doesn't say how far off this study is from the true parameter value. We can't really know how far off this study is because we don't know the true parameter value. Instead, the margin of error says how much variability there would be in estimates obtained from many similar studies. So how do we calculate these confidence intervals? Well, we use the sampling distribution to find out how much variability there is in the sample statistic. Then we choose a range of the sampling distribution that covers the confidence level we desire. Usually this is going to be 95%. Remember the empirical rule? That says that about 95% of the data are going to fall within 2 standard deviations of the mean. The confidence interval idea is similar. We find the range that covers about 95% of the cases. That is, we choose confidence intervals so that about 95% of the time, the range that we get for our confidence interval for any given study is going to include the true parameter value. That means that about 5% of the time, the true parameter value is going to be outside of our confidence interval estimate. Of course, we don't know which confidence intervals do and do not include the true parameter. If we did, we wouldn't need a confidence interval. Confidence intervals follow this general form. It's the estimate plus or minus the margin of error, which consists of the critical value times the standard error. Remember, the standard error is the standard deviation of our sampling distribution. Remember the critical value? This is the value of a random variable that corresponds to a particular cumulative probability. If we want a 95% confidence interval, we'll need to find the critical value of the relevant sampling distribution that corresponds with a mid-range probability of 95%. So why choose 95% for the confidence level? Well, this is actually somewhat arbitrary. You want a rather high number in order to limit the number of studies in which you think you have a good estimate, but for which your interval doesn't actually include parameter. But if you keep increasing the confidence level, your interval has to get bigger and bigger, since there's always a very small chance that the parameter could be far away from the sample mean. And the higher the confidence level, the faster the interval increases. In practice, people seem to find that 95% works rather well. So let's take this general form of the confidence interval and make it specific for 2 different population parameters. First, let's look at the confidence interval for a proportion. Remember, we take our point estimate plus or minus the margin of error, which is some critical value times the standard error. In this case, our estimate is the sample proportion, p hat, and we'll take our critical value from a standard normal distribution. The 95% critical value for a standard normal distribution is 1.96. And do you remember the standard error for a sample proportion? It's the square root of p times 1 minus p divided by n. Now that p in the standard error is actually the true proportion in the population, but we don't know the true proportion in the population. So we'll estimate the standard error with our point estimate based on the sample proportion. So putting all of that together, the confidence interval for proportion is our sample proportion, or our point estimate for the proportion, p hat, plus or minus 1.96 times the square root of p hat times 1 minus p hat divided by n, the sample size. What about for a mean? We take our point estimate for the mean, mu hat, and we add and subtract the margin of error, which is going to be the critical value for the sampling distribution times the standard error of the sampling distribution. So in symbols, we have mu hat plus or minus t star times the standard error. What was the standard error for a sample mean? It was sigma, the standard deviation of the population, divided by the square root of n. But similarly, we don't actually know the standard deviation of the population. So we'll use a point estimate for that as well, based on the sample standard deviation. So our confidence interval for the mean is our sample mean, mu hat, plus or minus our critical value, t star, times our sample standard deviation, sigma hat, divided by square root of n, the sample size. The t star here is a critical value from a t distribution. The t distribution is what results when you compute a standardized score, or a z-score, for a normally distributed variable using an estimated standard deviation instead of the true standard deviation. Remember, when we compute standardized scores, we subtract the mean and we divide by the standard deviation. But if we don't know the true standard deviation, we have to use an estimate. When we do that, we no longer have a normally distributed variable for our standardized score. Instead, we have a standardized score that follows a t distribution. Since we usually don't know the true standard deviation, we have to use the estimated standard deviation in the computation of our confidence interval, which means that our critical value needs to come from a t distribution instead of from a standard normal distribution. Critical values for t distributions can be found in the table in the back of the textbook.